users in the second phase who will contribute to estimate the frequency. So in the second phase, each user will first intersect the private value with the 2K atoms, so that each user will have at most 2K atoms, right? Because there is an intersection. And after that, each user pair to 2K and randomly select one and then report. Yeah, so we took a closer look at the approach and found that this approach can only find the frequent items and leave the frequent item set as an open problem in their paper. And secondly, it does not choose optimal solution in some settings. So first of all, the value L affects the error in the two ways. And secondly, the sampling also has a privacy amplification effect. So those two are our observations, and we will take a look at that. So the first observation is that there are basically two phases that will add noise. One is this reporting or perturbing thing of the frequency oracle. Another is that because the result is multiplied by L, the variance is multiplied by the L squared, which is quite bad if we use a very large L. Yeah, so another source of error is that if a user has many items, the truncation may make this biased. So there are basically two errors that L will affect. So it may be a trade-off how to choose L, right? So the larger L, the larger the variance, but the smaller L, the larger the underestimation. But it turns out that depends on the goal of our setting. So as we can see, we have two options. First is to set L to be quite large. Another is to set L to be quite small. So the bad thing about the approach to the left is that some users may just report dummy, making the overall signal very weak. And the observation of the right approach is that even if each user underestimates its atom sets, the relative ranking of the atoms are pretty stable if we have many users and a lot of atoms. So as a result, when the goal is to identify a set of candidates in this problem, we propose to use a smaller L. So another observation is this privacy amplification effect under sampling. So we already know that in the traditional LDP or in the simplest setting, we have this bound. But after a sample is involved, this thing might be different. For example, if we think a randomized response is used, the probability will be the probability of perturbation multiplied the probability of the sampling. So as a result, if we examine this probability carefully, we will see that if we use randomized response and we want to use epsilon as the privacy budget, the epsilon prime that is used by the randomized response can be actually larger than epsilon, which is some benefit by the sampling step. Yeah, so in our algorithm, we choose to adaptively choose better frequency oracle based on variance. But here, the randomized response will have a strictly lower variance. So that may change the guideline. So as a result, there is this swim method, which has 3 phases. The first phase is to identify the identify the candidates, but only let L equal to 1 compared to a very large L. And the second phase is also the estimating the the second phase will be to estimate the length distribution. Instead of using 2K in the surface, we will use L, which is 90th percentile in the surface. Yeah, so this is a basic diagram of the approach. Note that the top half are for the frequent item mining, and the bottom half is for the atom set mining, which will be more have more detail in the paper, but I will not cover it here in the tutorial. Yeah, so some empirical results that show that the some utility will be multiplied by 3 times if we take this approach. Yeah, so with that, I finish my part, and I would like to take any questions. If not, I will hand over to Graham.
One hour. That's so much time. Great. Okay, can you make it appear? That would be useful. Yeah. Beautiful. Okay, so let's wake up from our post-lunch slumber and recap. Where are we? So we're looking at this model of local differential privacy. We've motivated it through the real-world deployments, and Tanhao has taken us through everything from the initial definition through the basic mechanisms up to applications like finding frequent items and frequent item sets distributed over your population. So this next large chunk, we're going to be looking at applications, other applications that have been studied in this LDP model. When we started looking at this tutorial, I thought this is great. This is a nice sort of self-contained, well-defined area. And then the more we looked at the literature, the more we found was out there that people have been looking at just over the last 2 or 3 years. So what I'm going to do here is introduce each of these applications and not get too deep into the technicalities. And that's partly because you don't need to get too deep into technicalities. A lot of the work in these papers is in defining and modeling the problem in such a way that you can then invoke one of the techniques we've seen already, and that's the bit that kind of gives you, at its core, the local differential privacy and solves the problem in question. So I'm going to run through each of these applications, and we'll see how we get on in terms of time. So I'm going to start with one of the sort of an application that's sort of at this boundary between directly picking up some of the existing techniques. In the area of text, right? So some of the basic applications we've seen of LDP have been in text, right? Apple want to identify what are the new words people are typing on their phones so that they can add them to their autocorrect dictionaries. Or more generally want to look at other aspects of language use over text, particularly from mobile users. So this is interesting because what we looked at before was data that was coming from we assumed the data was coming from a structured domain. We started off looking at a binary domain, then we said, what if it's some fixed D, and then heavy hitters over a slightly larger domain. Now potentially we're thinking about possibly very large domains, URLs that are drawn on alphabets, but potentially very long. So I'm going to try and briefly say something about a few papers here. I'm going to pick up on n-grams because this is closest to where we just left off with frequent items, heavy hitters, and frequent item sets. So this is exactly in this sort of data collection from mobile users setting where you're thinking about how do I learn what are the new popular terms that people are using, the words people have made up or the slang that I can add to my dictionary. So simplify by saying assume everyone's just got one new term. Not really discussed how you generalize that, but it's fairly easy to generalize that to multiple new terms. So as soon as you do that, you realize, well, it's another heavy hitters kind of problem. It's just a heavy hitters over words. And indeed, the way you model it looks kind of familiar compared to the way that Tian Hao was saying how you might search for heavy hitters over a large domain. I'm going to think of this really as sort of searching within a trie. Right? The words that I'm interested in, with a sort of a start word and an end word character over this binary alphabet are just sequences. I can conceptually think of a trie over these sequences where each internal node has a count that tells me how many occurrences there are. And what I want to do is explore this trie, sort of top down, to sort of find the heavy nodes within there. Right? And we have this prefix property that says if there's a heavy node internally, then all its ancestors must be heavy. So it leads to a fairly immediate search algorithm, start at the top, descend down. The question is just, well, how do I make sure that this meets local differential privacy? So this priv tree approach uses multiple rounds. That's a distinction we haven't seen as much before. So most of the techniques we've talked about already are ones where we agree what the protocol is, the users look at their data, formulate a message, and in sort of on a one-time basis send that out. The aggregator combines those. So PrivTree says, well, one thing we can do that gives us a bit more flexibility is actually have rounds of interaction. Right? That some users make some initial statement, the aggregator observes that, and then poses a query out, and other users respond to that query, and you go back and forth. Right? So in some cases, it's clear that is a really useful addition. In this case, you might be able to get something comparable without interaction, but it's perhaps conceptually easier to think of this algorithm as an interactive one, because you really think of it as saying, round one, I'm going to start at the root and ask my population to tell me information that's going to determine what's happening at the next level, and then decide whether to expand that level or not, and so on. Okay. Another thing that we've seen in a different form already is to try and optimize the accuracy. There's this idea of breaking, rather than asking all users all queries, you partition users into this idea of batches or groups, and you ask your queries to one batch at a time, and each user only gets asked one question. And essentially, this is just an observation based on how you analyze the accuracy of these protocols, that you end up with more accuracy asking fewer users once than asking all users lots of queries. One other trick that you can do here is, and this is an idea that Michael's nodding at the back, you'll have seen before, is apply consistency ideas, right? So that if you're searching any kind of hierarchical structure, then there should be some properties like the sum of the child nodes weights should add up to the weight of the parent. You can formalize that. Because you don't have that property in what you observe because of noise and sampling error, you can then try and enforce that. You can try and say, well, given my noisy observations, what's my best estimate that is consistent? You can pose that as an optimization problem and solve that. Okay, so all that's saying is, there's one technique that was searching for frequent n-grams over text, and it was sort of pulling out a whole, a bunch of ideas and putting them together to achieve that. So here's a different formalization of a problem with text. So rather than just say what's happening in my dictionary, you could say, well, I want to build the autocomplete model. I want to build the statistical model that says, given what someone's typed already, predicts what the next word is going to be. Right. So if you're going to do that offline without privacy, you would get into the world of natural language processing and statistical modeling. You'd try and think, what's the best statistical model that looks at what someone's typed recently and makes a prediction? You'd come up with some kind of Markov model that says, look at the last 4 or 5 words, and then based on some very large corpus, make that prediction. So what's interesting is this is the right thing to do without privacy. It's the wrong thing to do with privacy. Because if you're thinking about learning these statistics, then you have very small support. Right? If you look over your population, even if you've got hundreds of thousands or millions of users, if you look at sort of the order K combinations of words, you have maybe only a couple of examples. Right? And as soon as you start adding the noise for privacy, then your accuracy on those goes down. So you want to sort of change how you look at this problem and think, what's a different model that I can learn that will be well supported by the data that I have access to? So what this paper proposes, it's a very short paper from this year, it picks up a model called tags and words that basically says, I'm going to predict the next word based on just the one word that came before it, plus what I think the part of speech is. So do I think the next word I'm going to see is a noun or a verb or an adjective or a preposition? Right? So I'm going to predict what the part of speech is by looking at the previous 2 tags of parts of speech, the previous 2 words. That's going to inform what word I think comes next. So it's also a Markov model, but it's a Markov model over a slightly different space. Why is this suitable? Because you need much fewer statistics to build. It may be that you can get this part of the model about what part of speech you expect to see based on the previous 2 parts of speech offline. You may be able to learn that without privacy. And what you do need to learn then are just essentially statistics on pairs of words, which is going to have better support over the data you have available. So it's an interesting paper in the area of LDP because the local differentially private part is sort of almost not there at all. Right? The local differential privacy part is just saying, once you've got your model to the point of saying, this is the statistics that I need, then you say, well, that's a frequency oracle problem. We're not going to reinvent the wheel, we're just going to take that out of the existing literature. So it's saying that there's lots of work to do in this area of privacy, where most of the work is more at the end of choosing the right statistical model for your data and reducing it to, let's say, a frequency oracle problem. Right. So it's all about thinking, how do you design the models so that you can instantiate them as accurately as possible? Okay. So if you think about what frequency oracle tells you, it says you have data essentially over a large one-dimensional or large set of categories, let's say. So sort of one-dimensional in some sense. More generally, you can look at multidimensional data. This is a paper that we presented yesterday, so I'm going to try not to dwell too much on this. Just to say, you can start thinking maybe this is one problem in terms of marginals, where you have users who have different attributes. For simplicity, let's just think of those as binary. And from these, you're interested in saying, if I take particular combinations of attributes, what is the distribution I see over those combinations? More generally, you could start thinking about all kinds of other statistical questions, more than just simple frequencies, and think about how would we materialize those under local differential privacy. So in the interest of time, I'm not going to say too much about the techniques for that problem. Just ultimately, they rely partly on frequency oracles. But again, it's frequency oracles on what? On what view of the data will you build the frequency oracle? Will you build the frequency oracle on sort of the full joint distribution? Will you build the frequency oracle on arbitrarily chosen or randomly chosen marginals of the distribution? Both work and both have different trade-offs in terms of accuracy. What we ended up doing actually in the paper was looking at essentially frequency oracles on transformations of the data. We were looking at the Hadamard transformation of the data. And again, there's a long history of Hadamard in local differential privacy and actually Hadamard in centralized differential privacy. So it's not coming completely out of the blue. But I'm not going to say too much about that. I'm just going to sort of move on a bit and talk about other aspects of marginals, and in particular, why would you be interested in marginals? I guess sort of one thing to say is there's a couple of other works that looked at marginals. So one of the papers that sort of proposes a generalization of the rapport system from Google, one of the things they do as sort of a subroutine is look at two-way marginals. And essentially what they do is they say we're going to collect data from individuals that has noisy information on pairs of attributes, and we're then going to apply a statistical inference process, in this case it's expectation maximization process, to try and denoise that over the population, so to try and learn the marginal from those reports. Another paper more recently, just published in a journal, says, well, if you look at higher order data, you run into a scalability issue because higher order marginals, potentially much larger numerical objects, except that from the data that you collect, you only get so many reports, so you're relatively sparse. They propose a sort of essentially a regression method that enforces or sort of takes account of that sparsity in order to do that. So I think it's fair to say these are both somewhat heuristic, but somewhat effective in practice for building marginals. And then you might say, well, why do I want these marginals anyway? So one reason is just because they're interesting statistical properties of your data from your population. But more generally, you can actually use marginals as a key component in building a model for your whole data set, right? So in general, over data with a large number of attributes, it's common to assume that there are sort of conditional independencies amongst those attributes. So you can build an effective model for your whole data set or your whole population data based on some model that says I don't need to know the correlation, the marginal of every single attribute together, but I can look at just a small number. I can sort of factorize my data into a smaller model, some kind of Bayesian model. So we looked at something where we looked at sort of a tree-structured Bayesian model. More generally, once you've got marginals, you can kind of use them to pick out what's a Bayesian network that seems like it does a good job of representing the data. Use the information from the marginals you've collected to choose what model you're going to build. Then once you've chosen your model, you can just turn the handle on it and generate synthetic data. And it's very attractive to generate synthetic data because then you can say, right, now I've got some synthetic data that hopefully looks like the data coming from my population, and I can do sort of anything I can imagine with that. So I can do any kind of machine learning task on that synthetic data and hopefully get an answer on that is reasonably reliable. Okay. So I'm going to talk about a few other types of data. I'm going to talk a bit about spatial data. Again, very easy to think why spatial data is something that you want to provide privacy for. But at the same time, we want to know how people are arranging themselves within space. And this is something where we can take inspiration from the centralized model. Right? So there's been quite a few papers in centralized differential privacy say, assume you start off with points in some two-dimensional geometric space. What is the kind of way you would represent that? And essentially, most suggestions involve some kind of hierarchical decomposition of space, either a uniform grid or an adaptive grid. And if you think about what that's doing, that's just building some kind of structure, some kind of histogram, really, within which you're collecting counts. Right? So when you transpose that to the local model, you're similarly trying to identify, buckets in a histogram and associate counts with them, so it's a frequency oracle or a heavy hitter kind of problem, once again. So the reason you might want to sort of not be quite satisfied with that is, one, if you start with a sort of relatively naive, uniform division of space, then that doesn't quite work, because in some regions things are very sparse, in other regions they're very dense, and you want to be a bit more adaptive to the occupation of your space. And another one is, it shows that sometimes this definition of privacy is perhaps a little bit too strong. So I might say, look, it's fine. I'm going to tell you I'm in Texas. Don't want you to know exactly where I am in Texas, but I'm fine you knowing what state I'm in. Someone else might say it's fine that you know that I'm in Houston, but not exactly where in the city I am. So a paper from a couple of years ago suggested a relaxation of the differential privacy model that, to a rough approximation, says each user, you think of imposing some kind of hierarchy over locations, maybe a semantic one that says, you've got countries are divided into states, states have cities within them, cities are divided into some subunit, and each user might sort of specify within this hierarchy what level they're comfortable with being represented at. And then you can just take the definition of local differential privacy and kind of align it with that basically says, rather than looking at the ratio of probabilities of the true answer to any other output, you can just restrict that requirement to say that the ratio is enforced between the true output and other outputs sort of within that level of comfort. Once you do that, then most of the work is done. You can define essentially sort of a modified version of the frequency oracle that, given a user's input, they pick where they're going to be represented within their appropriate level. Okay. So what you'll see is as we go through these examples, essentially over the last few years, people have thought about different kinds of data, thought about the properties of that data, the qualities that you want to have in your output, and thought about how you might achieve them under this model. So the next one to think about is social network data. So our true social network, who I actually talk to, that is still something that's quite private. And again, you can look to the centralized model and say, well, what have people done in the centralized model? Because for sure we know that's also going to be sort of a yardstick for what we can hope to achieve in the local model. Right. It turns out graphs and social networks are one of the hard problems in centralized DP. Right? So it only gets harder with local differential privacy. So what we're going to do again is go back to this sort of statistical view that says, well, we can't really hope to release a graph that looks almost identical to the true graph, because that is going to be far too revelatory. Right? It's going to have far too much information about who knows who. So what I'm actually going to look for is to release statistical information that lets me build a model so that I can generate a synthetic graph, so that that synthetic graph hopefully has enough properties in common with the true graph that I can meaningfully do analysis on that synthetic graph. Okay. So we also need to think about what's the application of the LDP definition to graphs. If you think of LDP as a definition over users, then you'd say, well, it ought to be that the information I reveal about one user, which might be one node in a graph, should look sort of more or less the same, whatever, if I just completely change everything about that user. You quickly realize, though, that that's going to be really tough to stick to and get anything useful out of this. So again, you get a relaxation. Here the relaxation you get is one often called edge privacy, or edge, in this case, local differential privacy, where I say, okay, the user is my unit, but I'm going to only enforce the differential privacy definition up to sort of addition and removal or change of one edge instant on that user. So it's certainly a weaker definition, but that's where we are. That's sort of the state of the art. So there's a paper last year in CCS that was thinking about how would you release social graph data, social network data. And it starts by saying, well, what are the kind of things you could do? At one extreme, you could think about the adjacency list of each user. That's a binary vector. So you could run, essentially run sort of randomized response on every bit in that vector. That would meet this edge differential privacy guarantee. But even that would be really bad for accuracy because you just introduce lots of noise. Right? And it's getting back to that problem we talked about before, that the presence or absence of each edge has very low support. It's just supported by one user. Right? So of necessity, I'm only going to get low accuracy if I view data at that fine level of detail. So another approach you could take is to say, okay, well, I'm going to aggregate locally, and for one user, I'm going to reveal information about their degree. How many other nodes do they connect to? Under this model of edge LDP, you can do that fairly accurately. And you can then plug that into some graph model that uses degrees, but then you'll say, well, I've kind of given up a bit too much, too quickly. Right? It's your sort of Goldilocks effect. The one method is too detailed, the other method is too coarse. What's going to be just right that sits in the middle? So again, this paper, and the great thing about all these things is there's maybe one or two references on any particular topic. So if you're inspired by this to go away and think about these problems differently, there's a wide open area to work on here. So this approach basically said we're going to try and find a representation of graphs where we have somewhere in between just degrees and full connectivity information. So essentially what you want to do is say for each node I want to represent some feature vector. And the trickiness here is you have sort of a bootstrapping problem of how do you define a feature vector for a graph where all you have to begin with is each node knows just its neighbors. So the way they bootstrap that is they say, well, we're just going to define our features based on picking a random subset of nodes, and your feature vector is for each subset of nodes, how many edges do you have to that subset? Right. So you do that once, and for each node, you sort of randomly pick the nodes. You release that noisy histogram for each user of their links to that group. And that's, it's not really very great because it's random, but then what you can do is you can do a few iterations. So you can essentially sort of say, okay, well, based on this random partitioning of nodes into sort of white and black groups, I see that some nodes do have a bit of commonality, so I'll group those nodes together, redefine my groups, say, okay, now these groups, let's call them sort of the white nodes, the grey nodes and the black nodes are my groups, and now I'll get everyone else again to reveal their noisy histogram to each of those groups. So you sort of do that one or two times to build this feature vector that you can then use that to instantiate this random graph model. Okay. So I've started talking about feature vectors. So obviously I'm going to now drift into the world of machine learning. And again, machine learning, very natural. Lots of problems people are interested in where we want to build models and instantiate those models based on learning from real data. Right? So pick any problem that you like, classification, regression, recommender systems we're going to see, and think about how would you build that model from data that is owned by individuals and held in this LDP setting. Right. So it seems a little bit tough because a lot of the methods you see for building machine learning models assume you've got your training data, that you can work on that intensively and evaluate the quality of your model. But so one trick, one nice observation is to say, well, we can sort of partition out these machine learning problems, right? So if we think of our input data as being a number of examples or data points, where each data point is, some feature vector x and some label y, then quite a number of machine learning problems you can write as an optimization problem where you're saying, I want to learn some parameters theta to minimize a loss function. That loss function is a sum over the loss for each individual example plus some regularization penalty. Okay, so we're not going to fixate too much on exactly what's going on here, but just say, the first observation, say we can take our objective, which is to find theta, and say that the way we figure out if we've got a good theta or not is based on summing over all the different examples. So this is true for linear regression, with or without ridge regression, with or without a quadratic penalty. It's true for SVM without kernels. It's true for a few other examples. So there's some hope here, but still, this says that if I guess some parameters, I can evaluate the quality of those parameters by sort of going out to my users. But how do I choose those parameters? Well, one thing we know about machine learning is this idea of gradient descent. That's how many of these things are done centrally. And what's gradient descent? Gradient descent says, pick one of your data points, starting from whatever model you happen to have at the moment, and figure out what's the gradient of this loss function for that data point, and update your model by taking perhaps a small step in the direction of that gradient. Okay? So this is something that looks like it would fit into LDP, right? Because I can sort of one example at a time, I can tell a user, right, here's the current model, here's the current parameters theta. You evaluate the true loss function and the true gradient of that. Then, this is sort of a vector release problem which we talked about briefly. There's a vector of dimension d, which is the sort of size of the data, the dimensionality of the data. So tell me about that gradient. Okay. Well, if I do it one user at a time, that's not going to be very good because I'll get mostly noise. But I can do a bunch of users at a time, and that's good because it's got a name in machine learning. It's called mini batch. And now I just take as many steps as I want, one batch of users at a time, to tell them here's the current model. Each of you work out your local gradient. I'll take the average gradient vector across that batch. Enough of the noise should cancel out that I'll make reasonable progress. Okay. Then sort of one last twist on this, which is if your D is very large, if the dimensionality of your data is very large, this won't work so well. But we can use this sort of technique called dimensionality reduction, right? I can say, rather than work in this sort of high-dimensional Euclidean space, I can pick a random projection, project my data down to that lower dimensional space, effectively project my model down to that lower dimensional space, and do all of my calculations and all my activity down there. And basically that all works. Okay. So what you notice about this approach, though, is it's in this sort of mini batch model where I'm having to have multiple rounds of interaction, right? I'm going to sort of start with a bunch of people here, take one step, then take another bunch of people over there, another few people. So there will be lots of rounds of interaction to do this. So it relies on being in a situation where I can rely on my user population sticking around and being responsive to queries in a sort of an interactive fashion. So there has been some work, mostly in the theoretical community, to say, well, what can you do without interaction, with sort of a one-time communication, or maybe a small number of rounds? So I'm not going to sort of talk through there. Just say, over the last year or so, people have said, do you need interaction? How can you do interaction effectively? And just some very recent work trying to sort of improve on even these results. I'm going to try and sort of skip ahead because I'm sensitive that we're running out of time. I'll just say one very brief thing about recommender systems, which is this is another kind of machine learning problem where you need to take some time to sort of set up the problem, But once you kind of work through all of the algebra, once you work through the structure of this problem, what you get to is something similar to before, which is you want to take a current model and incrementally update it based on some kind of gradient descent approach. So again, there's a paper in TKDE this year that sort of outlines an LDP version where most of the work is to get you to a model where you can apply this sort of vector release problem. You're going to ask a small group of people to evaluate a function that happens to be a gradient function and average their results to tell you what step you're going to take. So as we sort of step back and pull all these things together, what we see is there are some commonalities here, right? That often the challenge is, at this level, is not necessarily come out with a new mechanism or a new sort of generalization of randomized response. It's a question of building the right statistical model of the data so that that model is well supported, and then we can just reduce it to a frequency oracle or a vector release kind of problem. And across half a dozen different examples, maybe a dozen different papers, we saw the same ideas several times, right? That you want to split users into batches. You want to sometimes use multiple rounds rather than a single round. Finding the right transformation of the data, or use ideas like dimensionality reduction to reduce the amount of noise that you incur. When you have them in forced consistency constraints, just get that little bit of extra accuracy. Okay. So in the remaining sort of 5 or 6 minutes, I'm going to think a little bit about a few open problems. So here's a generic open problem. Take your favorite data analysis problem and say, can you do this under the LDP model? Right. So you can think about sentiment analysis under local differential privacy, trajectory analysis, social data analysis, all kinds of things. Or you could do something more challenging, that's challenging even in the centralized DP model, which is say, well, what about other kinds of less structured data that we still don't have a good grip on in terms of privacy? What's the right model to represent data that's more reasonably in the form of free text? What's the right model of privacy that lets you handle, photos and videos? I don't think we have a really good answer to that yet. And there's also sort of an algorithm engineering direction to this, which is to say, let's sort of think about how do you build a toolkit or other tools that help people use and understand local differential privacy. Right? We have a starting point from the open source release of Rapport, but that's somewhat specific. Could we build a sort of a more generally applicable toolkit? So that's sort of the obvious stuff. Let's think about some of the other directions. So one thing was mentioned before the lunch break, which was evolving data, right? We're typically interested not in a one-time data collection, but in going back and collecting data every day. And the way it's currently handled is at best heuristic, or with a relatively weak guarantee. So I said there is one recent paper that attempts to formalize that in a relatively theoretical way. But that's just one starting point. I think more generally, this question of evolving data is a big open one, within privacy in general, but in particular for local differential privacy. Okay, so I talked about machine learning. Whenever you talk about machine learning, sort of the elephant in the room is, well, what about deep neural networks that are just amazingly good at improving accuracy? And they are particularly challenging, I think, for privacy. Because, while it may seem that the parameters of a deep neural network model learned on private data are kind of inscrutable, we know that there are a lot of parameters and they capture subtle details of the data that may be revealing about individuals. Right? There may be parameters in these models that have millions or billions of parameters that are really specifically learned and saying something about just one or two examples. So in order to make a strong statement that says this model that I'm going to release is private is not revealing something requires a lot more effort, right? There may be some mileage in thinking about recent works on federated learning. Federated learning is a fancy way of saying, essentially the algorithm we just talked about for learning models, which is that you take your current model, you send it to users who locally tell you gradients. But if you only do that and you don't add privacy noise, then even gradients can be revealing. So again, there's some recent work, very preliminary. This is really in the central DP model, trying to think about how you would learn certain kinds of models without losing accuracy. So is it at all feasible to think about some kind of good neural network-based model that would still have a privacy guarantee? I'm not sure. There are deep theoretical questions here, and indeed, we didn't really get the chance to go into much depth on this. But one of the reasons that local differential privacy has attracted so much study is that maybe 5 or 10 years ago, there are a few papers came out from the theory community that sort of suggested this was something interesting. So in fact, for 10 years, we've known a characterization of what is the expressivity of the LDP model, right? It's equivalent to a model of statistical queries, right? But it's in this sort of polynomial view of complexity that says we know it's equivalent up to a polynomial blow-up in the number of users who participate in the protocol, right? Well, from our perspective, we've been interested in trying to optimize sort of small constants. So a polynomial blow-up would be a really dreadful thing in practice. So we have a theoretical understanding, but we still want to sort of understand more pragmatically for individual problems how well can we do on them. So there's lots of theoretical questions that you can think about. What are lower bounds for these problems? We often give upper bounds, but we don't always think as much about lower bounds. Are there problems that don't have any efficient LDP protocol? And the slightly subtle question here, how much communication is necessary? There's actually a large, we know several examples where essentially the algorithm has each user output only one bit that depends on their data, maybe some additional logarithmic number of bits that tell you what that one bit is telling you about, but only one bit that depends on the data. And is that true more generally? So a large category of algorithms that only need a tiny amount of noisy private information to be released. And just sort of say briefly on these things. In the centralized differential privacy model, there's a standard generalization that takes that multiplicative part of the guarantee and says, oh, in addition, you can have an additive delta. I think you can sort of fairly naturally apply that to LDP, and it doesn't really make a fundamental difference to the theory. But you could still ask, is it a useful relaxation for practical applications? And we've talked a bit already about multiple rounds. Do multiple rounds definitely help you in some cases? This is exactly the question that those theory papers in the machine learning area were trying to tackle. They were trying to say, do you really need multiple rounds to do machine learning? Can you do it with just a single round, and what's the cost? And you can look at other models, maybe. So think of this maybe sort of as a partial relaxation or a compromise between central and local DP. So in local DP, I don't trust anyone. I'm going to do everything myself. In centralized DP, everyone absolutely trusts the central aggregator. What can you do if there's sort of a trust model that says, well, this group over here, we trust each other, or we trust our local aggregator. That group over there, they trust their aggregator. And each group is going to then sort of do some local aggregation, release information, and then you'll aggregate for a second level. So another sort of take on this sort of hybrid privacy, you could say, well, what if you have some users who are paranoid, who want to work in the local model, other users who are relaxed, and will happily give up their data to a central aggregator. So there's this paper on blended privacy last year that said, well, here's one thing you can do. This is joint with, I think, Mozilla, who built the Firefox browser. So they're thinking about having some kind of, I guess, beta test group of users who share their data freely, and other sort of regular users who might opt in. So the opt-in users share their data freely. Some regular users who run under an LDP model. And they're using this for sort of a query answering ranking problem. So that's just one example of what you might do in that model, and you could think of other generalizations, right? What if each user just picks what subset of information are they happy to reveal, what information do they want to protect under LDP? We mentioned this briefly at the start, so I'm not going to say too much, just that, you know, what LDP is trying to achieve is a shift of trust. It's trying to say, I want to remove my trust on central aggregator. Right? So there's other ways that you might achieve that shift in trust. So you might try and pick up ideas from security and secure multi-party computation, right? So I've seen quite a few different papers over the last couple of years that have tried to say, can we essentially take some differentially private protocol and run it so that we simulate that under secure multi-party computation? Why isn't that the state of the art? Why isn't that what Google, Apple, and Microsoft are implementing? Because it seems, you know, one, it seems fairly complicated, and the computational overheads of these SMC primitives, even though they're getting better, are still too high to make it practical. But, you know, maybe, you know, if we can get this right, if you can prove results in this setting, then you get back to sort of the error of the centralized DP algorithm, so you get a big improvement in accuracy. Okay. So I'm about out of time, and I do want to get some questions in. So I'll just sort of very quickly say, you know, yes, there have been these big deployments, but do reflect on the fact that your interaction with Apple, your interaction with Google, is still then going on wrapped in an encrypted communication that just goes to them. So you know, they are being very sort of selective about what they capture. They are choosing the epsilon value, and they're gathering lots of other information from you without any privacy protection. So even though there are these big deployments, there's still sort of questions around why are these companies exactly doing this? There's probably quite a complicated set of reasons about why they've chosen to do this for these particular measurements. And what happens when you aren't a major multinational technology company who can't rely on millions of participants who you can opt into this data collection? Could you think of a model of local differential privacy where people actually just publish freely? You know, I'm secure, I know that the algorithm works, so this is my LDP data for some aspects of some of my activity, and multiple aggregators could have access to that and do different kinds of analysis on that. I don't think we live anywhere close to that world, but you could think of, you know, a world where we had open source LDP data. Okay. So I'll just leave these conclusions up there because I think we're pretty much hitting the break right now. So I'll just stop there and ask if there are any questions about what we've covered. Thank you.
Thank you for your tutorial. Actually, it's very inspiring. So I'm working on this area. So one question about what we call interactive LDP, so multi-rounds. So one question that haunting me is that, well, when you for each round, you have to change the parameters sent back to users for the next round. So would that kind of updated parameters to be kind of a privacy disclosure? Because you actually you gather more information from the previous rounds, and then you can become more and more accurate. But eventually, actually, the second batch, third batch users actually get more information of that.
Yeah. So I think you can relax because it comes back to some of those primitive properties we had at the start around composition, but also sort of the freedom to do post-processing. So, you know, just think about that very first batch of users. the aggregator asks them some query, they each run a protocol that is locally differentially private with a parameter epsilon. And in many instances of these interactive, multi-round LDP things, it happens that you ask each user to participate once and then they kind of go quiet. So that makes it easier to think about, because what's really happening is you're asking the user some question, and the aggregator can ask pretty much any question they like. And if the user follows the protocol, then they know it doesn't matter what their answer is, it doesn't matter, what the question was, they know that they have this local differentially private guarantee around their response. So there really isn't any leakage not allowed by the model at an intermediate point on this protocol. What you might be touching on is a more general question in privacy, which is, if I build some model of my users, if I build some model of my population, I can do so under whatever privacy model I like, centralized DP, local DP, whatever. And I get that guarantee. I still have to ask the question, am I happy with that guarantee? Right? So it may be that the model that I build exactly meets, the way I build it exactly meets the differential privacy guarantee, but it still informs me something about the world, it still informs me something about the population. And you have to sort of accept that that model might reveal something about the world that you weren't expecting. Right? So, I might build my statistical model about the relationship between smoking and a disease, and I find, yes, if you smoke, you're much more likely to have this disease. Right? That's true, and there's a large statistical base to support that. I then might find someone who smokes and say, right, now that I have this information, I'm going to change my belief about that person. I'm much more likely to believe they suffer from this disease. Right? We learned all that completely reasonably, and that person may not even have been participating in the data collection or in the process, but my beliefs have changed as a consequence of what I've learned statistically about the population. But either you worry about that, in which case, I think your model of privacy is tell no one anything, or you accept that and you say that is just part of learning more about the world.